Hello everyone, I'm Andrea Arduino from Turin and I'm going to present my work on the origin of divergences in a time-dependent orbifold, which I did in collaboration with Riccardo Finotello and our supervisor Igor Pesando. We started considering the fact that string theory is a good candidate for a theory of quantum gravity, and so it should provide a satisfactory description of cosmological singularities like the Big Bang singularity and black holes. There has been a lot of work in the literature in this field, and it has involved the study of the so-called Minkowski time-dependent orbifolds, which have been well classified by Costa and Cornalba according to the Poincaré Killing vector, which acts as a generator. So the spacetime are known in the literature with the names of boost orbifold, null boost orbifold, and O-plane orbifold. What was found out, unfortunately, is that perturbation theory in these models seems to fail. In fact, the 4-point function of closed string tachyons seems to diverge in the range limit of high energy and small fixed angle. This is a very pathological behavior which has been interpreted as the result of a large gravitational backreaction due to the exchange of a single graviton near the singularity. What, however, has gone completely unnoticed is that even in the open string sector, if we consider the 4 open string tachyons amplitude, there is a very similar divergence. So, since we are working at a tree level, this suggests that the problem cannot be strictly related to gravity. And this is exactly the observation that motivated our work, where we first try to find out the real origin of this phenomenon, and then we try to present also 2 possible ways of regularizing the problem and of curing the divergences. The point of our discussion is that the root of all divergences lies in the non-existence of the underlying effective field theory. In fact, we constructed a scalar QED theory on the null boost orbifold, and we showed that the behavior of the eigenfunctions of the scalar D'Alembertian near the singularity is of this kind. This means that if we consider the product of n eigenfunctions, this would give a singularity which is technically not integrable. However, thanks to the exponential term, we could consider the interpretation as a distribution of this product of n eigenfunctions, provided that a equal to 0 is not an isolated point. Unfortunately, again, this is exactly what happens along the compact direction of the null boost orbifold, where a is proportional to the square discrete momentum associated with the compact direction. So we can therefore conclude that the fourth and high-order contact terms are indefined because of the presence of a discrete zero eigenvalue, and this is the real motivation of the non-existence of the effective field theory. Then we move to string theory, and from this point of view, we know that contact terms may arise from the exchange of string massive states. So what we showed is that the open string 3-point amplitude with 2 tachyons and the first massive state may be divergent if we consider some physical polarization. In fact, this is the behavior of the amplitude that we find out. This result suggests that first, string theory can't do much better than field theory when the latter doesn't even exist, at least at the perturbative level. And second, also that when spacetimes become singular, string massive modes are not anymore really spectator. In section 7, we also performed an analogous analysis on the boost orbifold, and we found out that very similar arguments hold also in this case. Since, as we have seen, the problems seem related to the presence of this compact direction in the underlying effective field theory, we constructed a new orbifold, the so-called generalized null boost orbifold, where there is a second Killing vector which acts as a generator. The key point is that now the behavior of the eigenfunctions of the scalar Lambertian in a scalar QED theory near the singularity is still of the same kind, but it's possible to write the phase factor A as a linear combination of the discrete momentum L and of a continuous momentum P, so that A is proportional to L plus minus P squared. This avoids the presence of isolated zeros and makes always possible the interpretation of a generic endpoint function as a distribution, which was not possible instead in the null-Boost-Torbefold. Notice that the generalized null-Boost-Torbefold is very similar, though not really equivalent, to the null brane which was studied by Seiberg, Moore and Liu. Another way to cure the divergences is to take into account that closed string winding modes may help, as was already suggested by Krabs and again by Seiberg, Moore and Liu, in analogy with what had been done in the resolution of static singularities. In fact, twisted closed strings become massless near the singularity, and so they should somehow be included in the theory description. We know that they generate a background potential, and from the open string perspective, this is equivalent to an electromagnetic background. So, in light of this, under a modification of the scalar actions, the problems may be solvable. This approach requires a deeper analysis, but probably it's the most natural and straightforward continuation to the work just presented. Thank you for your attention, and thanks to the organizer for giving me the opportunity of presenting my work.